Okay, then we can get going. Good morning, good afternoon, everybody. Thank you for attending today. Today is a new technology webinar number 4. We are really excited about the topic today. We have Thomas, we have Kelsey, really interesting topic. I just want to make 2 comments before we get going. The first one, we thank you everybody for joining the new technology webinars. The Geothermal Technical section has received the Technical Excellence Award. We continue to work for all our members. Geothermal is hot, so there will be a lot of content that we'll be deploying in the next 6 months. So thank you very much for joining the sessions. Number 2, please check our GTTS events website. We have the next webinar on August 24th, and we continue just delivering, transferring the knowledge between oil and gas geothermal industries. With that being said, Thomas, I pass it on to you. Thank you so much for the presentation, and I hope you enjoyed it as well. Kelsey, thank you so much as well.
Good day, hello viewing, and welcome to PwrCor's webinar presentation. And thank you to the Society of Petroleum Engineers for the opportunity to introduce PwrCor and its technology to the community. First, a little background on PwrCor's technology. PwrCor is a technology development company specializing in converting low-grade heat to power. The technology's basic function is that it uses free heat as fuel to produce mechanical power that can generate electricity. Benefit includes it offsets or eliminates the need to produce or buy electricity on site. It reduces carbon footprint and reduces the amount of heat that would have otherwise escaped to the environment. PwrCor has a novel heat engine design. However, converting heat to power is by no means a new industry. Power cycles using steam have been commercialized for well over 150 years, and cycles using organic fluids for over 60. PwrCor, however, uses a power cycle that is particularly effective at converting very low-grade heat to power, and is far more effective than others in these low temperature ranges. The amount of untapped low-grade heat is enormous, and the ability to use it economically as free fuel is a game changer. PwrCor's position is unique. We have found no competition in converting low and ultra low grade heat into power. PwrCor's technology is proprietary and developed in concert with engineers at the Southwest Research Institute in San Antonio, Texas. More about that a little later on in the presentation. PwrCor has a simple mechanical concept. We incorporate supercritical CO2 as a working fluid for our heat engine. The unique ability of supercritical CO2 to expand and contract in repetition when exposed to even slight changes in temperature is the premise for the power cycle. How is it better? PwrCor operation is similar to an organic Rankine cycle. However, by remaining in a supercritical state, PwrCor's thermodynamic cycle does not undergo the 2 energy-robbing phase changes that does ORC. This ability to economically convert low-grade heat to power can open up dozens of heat-to-power applications previously not viable for commercialization. Low-grade geothermal heat is just one example. Granted, other technologies exist to convert low-grade heat to power, but at what cost? The keys to the kingdom of low-temperature conversion is to do so economically. The amount of untapped low-grade heat is enormous. And as I said before, the ability to use it economically as free fuel is a game changer. Now on sustainability. Some of PwrCor's sustainable advantages over other technologies are obvious. But of note is PwrCor's small footprint as compared to photovoltaic and wind, and its ability to be situated at the demand site. Otherwise, unlike wind and photovoltaics, PwrCor can operate 24/7 and can also be coupled with battery storage as needed. When compared to ORC, CO2 is relatively inexpensive compared to ORC working fluids and is more environmentally friendly. To drive home the point on how much better PwrCor is, here is a conversion efficiency comparison showing PwrCor versus ORC. PwrCor's ability to maintain a supercritical cycle state means better overall process efficiency when compared to ORC. This, combined with supercritical CO2's thermodynamic properties, enable the PwrCor system to work with ultra-low heat temperatures, even as low as 140 degrees Fahrenheit, convert heat more efficiently than other heat engines, known as greater thermodynamic efficiency, and is up to 3.5 times more effective in converting heat input than other technologies. In thermodynamic terms, it has less exergy destruction than technologies like ORC. This graph compares PwrCor with two state-of-the-art ORC technologies, illustrating PwrCor's superior capability to generate electricity from low-grade heat. As mentioned previously, we engaged Southwest Research Institute, or SWRI, for our R&D and applications engineering. For those of you not familiar with SWRI, headquartered in San Antonio, Texas, they're an independent and nonprofit applied research and development organization. SWRI occupies more than 2.3 million square feet of office and laboratory space on more than 1,500 acres in San Antonio. For 75 years, Southwest Research Institute has addressed challenges from deep sea to deep space and pretty much everywhere in between. PwrCor's work with SWRI, however, is very specific and leverages SWRI's expertise in working with and developing supercritical CO2 power cycles, for which they are recognized worldwide. Now, I'd like to introduce Kelsey Katcher. Kelsey is a R&D group leader in the rotating machinery dynamics section of Southwest Research Institute. She will give you SWRI's perspective on what makes supercritical CO2 so effective, on the specific technology they've worked on with us so far, and on their overall supercritical CO2 research and testing experience and capabilities. Kelsey?
Hi, yes, thank you. That was a very kind introduction. I guess hop to the next. All right, so it's been mentioned several times today, and it's kind of a hot topic word floating around the industry, but SCO2. So what the heck is SCO2 in case you don't know? So the S here stands for supercritical, and then CO2 is just carbon dioxide that we're familiar with. So to present what the heck this is, I'm showing a phase diagram here. So I'm presenting pressure versus enthalpy. And then on this diagram, you have the two-phase region or the two-phase dome. Underneath here, all state points will be a mixture of liquid and gas. And then to the left, at higher pressures and lower temperatures, you'll have liquid phase. On the right side of the dome, at lower pressures and higher temperatures, you have gas phase. So this all, I feel like, is very intuitive. At the top of that two-phase dome, though, I have shown a star there. That's what we call the critical point. And then anything above that critical pressure and temperature is what we're calling supercritical. And so supercritical is actually its own phase, and it exhibits some qualities of a gas phase and some qualities of a liquid phase, but it's really its own thing. If you go to the next. Next. So one thing that's very useful or attractive with supercritical CO2 is it's very dense. So it's actually dense like a liquid, but it still fills up space like a gas. So having these high density values means you can have equivalent mass flow because power scales with mass flow, but at lower volume flows, which means you can have more compact turbomachinery, smaller pipe sizes, smaller heat exchangers. Also, CO2 retains high density values even at high temperatures. So even on your hot leg of your power cycle, so downstream, upstream or downstream of your turbine, you can still have small line sizes and you don't have to have these massive pipes that you would have, say, in a steam system or any other gas system. And overall, this means the energy density of CO2 in the supercritical state is higher. So comparing to ORC fluids, we're about 4.5 times higher energy density. Next, please. So if we look at the phase diagram again, the black lines on here are showing isobars, so constant temperature lines, and then the red lines are actually constant density lines. So if we look here at the density values that are close to the critical point and follow those over, we're about 40 to 70% the density of water. So we're still acting somewhat like a gas, but you have very, very high density values. Next. But in contrast, you have very low viscosity values. So again, comparing to water, we're about 8% the viscosity of water. So in these compact systems, compact passages through your heat exchangers perhaps, or smaller line sizes, you don't have to worry about really high frictional losses because your viscosity levels are very low. Next. And then the other thing that's helpful with CO2 specifically is the critical point is very near ambient. So these qualities aren't specific to CO2, but more specific to supercritical phase. So you can get similar benefits with, say, supercritical water. And we've looked at, or other researchers have looked at supercritical water for thermosiphons for geothermal, for example. But for example, the critical point of water is much less attainable. So for the critical point of water is actually about 3,200 PSI and 700 F, compared to CO2 is like 1,000 PSI and 88 F. So much more manageable pressures and much closer to ambient temperatures. The near ambient temperature also makes these cycles conducive to air cooled, so you don't need any kind of extravagant heat exchangers or coolers here. Next. So I mentioned more compact. So this is a graphic that you probably have seen floating around. It's very popularly used, but on the left is a traditional steam turbine for utility grade or utility scale power generation. So this is a 300 megawatt turbine. Diameters are about 20 meters, so very, very large. An equivalent power turbine with supercritical CO2 is about 5% the size. You can see it there. With the equivalent diameter or estimated diameter of about 1 meter. So much more compact. This lends to much less material, much smaller casing sizes, much smaller line sizes. So overall, less material, less cost. Next. So here's a couple real life examples. I think this is an equivalent turbine in the background. So that's a 300 megawatt steam turbine. And then in their hands would be like a 10 megawatt CO2 turbine. So just tiny. I mean, you can hold it in the palm of your hand. Next, please. Here's one more example. So this is actually the STEP facility turbine for our CO2 power plant that we're building here on our campus. I think this is a 15 or 16 megawatt turbine. But this is the full shaft. So you can see there's 4 axial stages, but this is including bearing seats, seal surfaces, and then thrust bearing seat as well. So that's the full shaft and it's maybe 1 meter long. Next. So when we're talking about supercritical CO2 for low temperature applications, basically we're comparing to ORC cycles. So organic Rankine are kind of the state of the art at the moment. So you can see a traditional ORC cycle here on the bottom right. Again, showing it on a phase diagram, but here we're doing temperature versus entropy. And then a simple phase or cycle diagram shown on the top right. So from state point 1 to 2, we're going across a compressor or a pump. From 2 to 3, we're adding heat. So you're following the red line up on the phase diagram. 3 to 4, we're expanding in the gas phase. And then 4 to 1, we're cooling back across to state point 1. So if you pop up my text, please. One more. Thank you. So one thing to note with the ORC cycles, and Tom mentioned this earlier, is that you're actually phase changing through both of your heat exchangers on an ORC cycle. So the Rankine part of this means that you're subcritical and you're traversing the dome. So whenever you're running through your heater following that red line, you're kind of heating until you get, so you're in liquid phase, you're heating until you start getting into the 2-phase region and start getting some into gas phase. And then as you're traversing the dome, you're moving at constant pressure and constant temperature, and then just converting to a higher gas volume fraction until you get to full gas phase, and then you start gaining temperature again. Next, please. The main problem with this is if you're following that temperature profile where you're increasing in temperature and then you're adding heat, you're continuing to add heat, but you're not adding any temperature, you get that knee right there in your temperature profile, which causes a pinch inside your heat exchanger. So if you have your ORC fluid following the blue curve on my small thumbnail plot, and then your main process flow, so heat rejection from your main process or your waste heat fluid, or this could be brine coming up from your geothermal well. As you're heating your ORC fluid, you're pinching against that knee. So you're not able to get as much temperature change in your process fluid, and you're not able to get as much heat into your ORC fluid. So that is really limiting how much power you can get out of your ORC cycle. Next. So when we compare to a supercritical CO2 cycle, again, if we look from state point 2 to 3 across the heater, on the phase diagram, we're showing that it's a linear path, but in reality, it's following that constant pressure line or the isobar from 2 to 3. So if our SCO2 temperature is following kind of the blue path on that thumbnail plot, and then your main process fluid is following the black curve, you don't have as much of a pinch, and likely you're going to pinch at one end of the heat exchanger or the other, but you're not pinching in the middle. So you can get a much larger temperature delta from your main process, which means you're getting more heat into your waste heat recovery cycle, so you can get more power out. Next. Next. All right, so then the main takeaway here is that because we're remaining supercritical with the CO2 cycle, you're not phase changing, you're actually remaining above the dome, so you're not pinching in your heat exchanger. That's kind of the takeaway here. Next. So if we're comparing, say, the PwrCor SCO2 system compared to an ORC, it looks something like this. So if you pull up the first plot here. Okay, so this is some published data from a commercial ORC and what they say that they can produce. So here we're showing hot water flow rate on the bottom right. So this would be the red stream in the cycle diagram at the top right. So we're sweeping hot water flow rate on the x-axis, and then the various traces are sweeping hot water temperature, so going from maybe 150F up to 270F. So if we look specifically just at the red trace, the dashed line is the ORC, and then the solid line is what we think we can do with an SCO2 cycle. And so as you're increasing your flow rate, increasing your hot water temperature, obviously you get slight increase in power output, but stepping from the ORC to the SCO2 cycle, you get a huge jump in net power output. So here maybe 2 or 3.5 times as much net power from your cycle. And this is just due to being able to get more heat into the cycle. Next. So similar results if we look at a separate ORC vendor. Here the results are presented a little bit differently, but hot water temperature swept on the x-axis, and then the various traces are cooling water temperature. So looking at the light blue curve on the cycle diagram, and then holding the water flow rates on the hot and cold streams, both at 40 liters per second. But here, still seeing very similar results where we're maybe 2 times as much power output using an SCO2 cycle versus ORC. Next. Next. So what it comes down to, and Tom alluded to this earlier, is that essentially it's a difference between thermodynamic efficiency and process efficiency. So thermodynamic efficiency is basically you have some amount of heat coming in at your primary heater. How much of that or what ratio of that is getting converted into usable mechanical or electrical power at your expander. And so when we're comparing an SCO2 cycle to an ORC, the thermodynamic efficiency is pretty similar. So the SCO2 is maybe a little bit higher, maybe 5% improved in thermodynamic efficiency. But the key improvement here is due to process efficiency. So because we're able to take more heat out of that process stream and convert it into usable mechanical or electrical power, I would say our process efficiency is much higher because basically we're able to take more heat or recover more heat from that waste heat stream or from that geothermal fluid coming out of the well. Next. Again, so due to mainly the size, because the energy density with SCO2 is so much higher, you have more compact equipment, more compact piping, more compact heat exchangers and turbo machines. So that brings our CapEx down. So maybe even a 50% reduction in equivalent size for SCO2 versus an ORC engine. Next. All right, so on the next couple slides, I'm just going to highlight some of the other things we've worked on at SWRI here in SCO2. So over the past 10 or 12 years, we've done a lot of supercritical CO2 projects for various scales and various applications. We've done a lot of cycle model and system designs looking at different cycle infrastructures and how do we kind of milk that heat addition and get as much out as we can. So looking at high temperature cycles, medium enthalpy cycles, and then all the way down to low temperature cycles. We've also done some work in oxycombustion, so where you're actually injecting fuel and pure oxygen directly in the CO2 stream, burning it there, similar to a gas turbine, but at high pressure instead of indirectly heating your cycle. So that's been interesting as well. Within all of these applications, we've done lots of turbine design, lots of compressor design. So looking at the aero path for radial and axial type machines. So aero mechanical, rotor dynamics, typical machine design. We've also done lots of component design specific to CO2. So looking at bearings and seals and the specific challenges you have here, especially as you get very hot, say at your turbine section, and then 3 inches away, you have your dry gas seal, which has to remain at maybe 200 F or below, right? How do you deal with that thermal transient? So specific challenges we've had to face there. But you can see some examples of our turbo machinery that we've worked on designing, building, and testing here at SWRI. We've also done a lot of work for design and optimization for heat exchangers for CO2 as well. Next. So a lot of the bigger test facilities that we have are designed specific to the recuperated recompression Brayton cycle. So this is a supercritical CO2 cycle, but a much higher temperature cycle. Next, please. So coming into your expander, we're at maybe 260 bar and 700 C. So this is looking at like utility scale power generation where you have maybe a fired cycle, or maybe you're using concentrated solar or nuclear, something like that, where you have very high temperatures and you can get much higher cycle efficiencies. So some of the facilities we've built around this, if you want to pop those up for me. The first is an integrally geared compressor expander. So here we actually have compressor stages and expander stages built on the same machine with a single bull gear. So on the full build there, this is a 10 megawatt frame. You would be directly coupled to a generator, an 1800 RPM generator, and outputting from a single frame with a very small footprint comparatively to a steam system or an ORC system. Next. This is another high efficiency compressor that we have worked on over the past several years is a barrel type machine. But again, looking at this CO2 cycle next. And then all of the work over the past probably 10 years has led up to the work we've been doing at the STEP demonstration plant. So this is a 10 megawatt net power plant that's actually built here on our campus, demonstrating this recompression cycle. So that facility is progressing and they're working through commissioning runs on the turbo machines, and they're looking to demonstrate simple cycle coming up this fall. So next. All right, so previous slide was a lot of high temperature work that we've done in CO2. We've also done some mid temperature and low temperature stuff as well. So on the top is a photo of a turbine skid we developed for an SCO2 geothermal cycle. So for that cycle, we'd be sending CO2 downhole, coming back up, running it with a thermosiphon. So we have just a turbine on surface and then relying on the density difference between the injection and the production leg to drive the flow. So here we've packaged the CO2 turbine on the left. You can see the barrel there. So the impeller itself is quite small. Bearing case sitting on those pedestals on the left of the skid, gearbox there in the middle, and then generator, the ABB blue generator here. And then to the far right, we have the lube oil system for this guy. So we have a fully packaged turbine skid here that's waiting on the facility so we can run commissioning there. And then below we have the PwrCor system. So this is a system we actually hooked up in our CO2 facility. We did performance testing on, and then after that was shipped to a demonstration site. So one thing we should note here is, so the PwrCor system is probably the lowest temperature system that we've demonstrated. We've done, like I said, lots of high temperature work, lots of mid temperature work looking at geothermal cycles and those kinds of things. But as far as low to mid, I think PwrCor is the main one that we've worked with. And I think that this could be applied as a bottoming cycle very easily to, say, a geothermal system like we've looked at, or even the high temperature systems. I think that's it for me.
Okay. Thank you, Kelsey. That was very informative. Good presentation. Okay, SWRI has explained the science supporting PwrCor's technology, done extensive testing with their world-class supercritical CO2 laboratory, and assisted in PwrCor's technology development. I might say from the beginnings of PwrCor's technologies, first used to power rigs on shallow stripper wells, to today, as we engineer our fourth generation systems, we have found SWRI to be an excellent and valued partner. Now that you have a flavor for the technology and how it works, I'd like to turn our focus to the opportunities it presents in geothermal and related applications. There is simply an enormous amount of wasted heat in this world. The U.S. Department of Energy cites that more than 2/3 of all applied energy is lost, almost all of it as heat, commonly referred to as waste heat. This heat has an immense and sustainable resource that goes highly underutilized today. Waste heat comes in many forms, from boiler and industrial process heat to engine waste heat and even low temperature geothermal heat. The Department of Energy has calculated that if waste heat from industrial processes alone could be converted to electricity, it would total 20 trillion kilowatt hours annually. This would amount to 5 times the actual total US electricity consumption in 2022. Approximately half of that wasted heat is in the 160 to 300 degree F range, which is PwrCor's sweet spot. Industrial wasted heat can be readily extracted from process cooling systems and exhaust chimneys. Other sources, such as lower temperature solar heat and geothermal, can also now be economically utilized. PwrCor opens heat to power opportunities previously not viable to many industrial applications, as shown here, and stands to dramatically impact their energy profiles and operating economics. Now, for some specific industrial oil and gas applications. Gas compression is a good first example. Gas compressors generate heat while cycling through the stages of compression needed to achieve desired pressure. Between stages, heated compressed gas is cooled before entering the next compression stage. PwrCor intercepts the heated gas destined for cooling and generates on-site electricity, and does so while reducing the cooling requirement for the overall compression process. Free electricity combined with reduced cooling demand results in significant operating savings in natural gas compression for upstream gathering and pipeline transportation applications, carbon dioxide compression for upstream enhanced oil recovery applications, and hydrogen compression for green or blue hydrogen production. As a point of interest, it should be noted that PwrCor is currently engaged in developing pilot installations for natural gas as well as CO2 compression applications. Other industrial oil and gas applications include hydrogen production, both green and blue, specifically waste heat from electrolyzer operations. We've modeled converting heat from the cooling cycles in both PEM and alkaline electrolyzers and demonstrated that significant on-site power can be generated. Also, the steam methane reforming process, SMR, offers low-grade heat-to-power opportunities, as well as the possibility of compressing carbon dioxide. Machinery operations, specifically heat-to-power opportunities in reciprocating engines, both gas and diesel driven, have also been modeled. Jacket water heat, oil circuit cooling, and exhaust heat all provide viable opportunity. Lastly, stranded gas, unused stranded gas or flared gas can be used to provide a suitable PwrCor heat source that can be used for on-site generation. PwrCor has identified several low-grade geothermal heat opportunities, some which can be readily deployed now. For immediate consideration is bottoming cycles for current US and global geothermal plant operations. Kelsey alluded to this previously. PwrCor engaged Southern Methodist University's Geothermal Laboratory to work with Southwest Research Institute to estimate the potential to generate electricity from return geothermal fluids from existing geothermal plants for which there was adequate data. It was determined that the potential from 31 US plants studied was 427 megawatts of additional generation. Global estimated PwrCor potential for this application exceeds 6 gigawatts. Next is the potential for future low temperature geothermal development. The number of known and projected low temperature geothermal locations targeted for ORC binary plant development far exceed the number of existing plants. PwrCor technology can be deployed to generate substantially more electrical power at a lower cost per kilowatt than existing binary technologies. Interestingly, there are various well-known studies that estimate the potential of these geothermal resources in the United States. However, most don't focus on source temperatures below 110 C or so, and all base their estimates on ORC technologies. PwrCor can dramatically change that dynamic. Lastly is the potential to develop dry or abandoned geothermal wells. Wells drilled and determined to not have sufficient thermal energy to run economically using existing ORC technology may be suitable for PowerCor operation. Similarly, existing binary plants abandoned due to degradation of the geothermal resource may be made viable with PowerCor. This can be an opportunity to convert a sunk cost into a productive asset. Lastly, keeping in mind that geothermal energy alone has the potential to provide for all the electricity needed annually in the United States, developing projects with PowerCor makes for much better economics. Now, to focus on geothermal opportunities in the oil and gas fields. First, on existing active oil and gas wells, and specifically from opportunities in heat from co-produced fluids to produce on-site power. Studies place co-produced water during oil and gas production at between 15 to 25 billion barrels per year in the United States alone. Explaining to an audience of petroleum engineers ratios of co-produced fluids to hydrocarbon production in the oil field, as well as the cost of managing co-produced fluids, would be like preaching to the choir. I'll focus instead on applying PowerCor's potential to a relatively recent study that estimates the near-term electricity generation potential from co-produced fluids. The study, entitled An Estimate of the Near-Term Electricity Generation Potential of Co-Produced Water from Active Oil and Gas Wells, was based on a sampling of 500,000 wells in the US, taken from a total of 2.5 million active wells. Of the 15 billion barrels per year of co-produced water accounted for in the study, approximately 70% is less than 257 or 125 C, and 48% is less than 176 F or 80 C, which interestingly was deemed too cool for ORC and subsequently not evaluated. The study estimated ORC power potential at 625 megawatts. In comparison, estimated PowerCor power potential is 2.5 times greater than ORC, approaching 1.6 gigawatts. This PowerCor estimate does, however, include potential from water temperatures between 150 and 176 degrees Fahrenheit, which the study deemed unsuitable for meaningful ORC generation. Now, let's go back to the well again, or perhaps back to the future, to see the potential of deploying PowerCor on abandoned oil and gas wells by exploiting existing well structures for inherent heat to produce on-site power. And specifically, the potential to use existing drilled well infrastructure to offset approximately 40% of the cost of developing a geothermal plant. According to EPA studies, there are over 3.5 million abandoned oil and gas wells in the United States. While not much can be readily found on the current thermodynamic profiles of these wells, however, assuming well thermodynamics as given in the co-produced study, the potential for PowerCor to use the heat from these wells to produce electrical power is substantial. Our calculations estimate potential PowerCor generation of 2.2 gigawatts. And I might say that is a conservative estimate. Now that we've gone over how PowerCor technology can be applied, let's take a look at economics. As stated, superior conversion efficiency drives better system economics and shorter payback periods. Projected payback period for commercial PowerCor systems are typically under 2 years and can be driven even lower with government incentives such as those provided by recent U.S. legislation offering up to 50% investment tax credits. Our studies predict production costs projected to rapidly decline, and we see a clear path to sub $1,000 per kilowatt pricing at commercial production scale. Lastly, our projected levelized cost of energy, or LCOE, is under 4 cents, which is competitive with solar or wind. As regulations push toward a carbon neutral economy, PwrCor technology is uniquely positioned to provide a sustainable solution that is economical and reliable. In summary, a lot of information was shared today, all of which we hope you found at least to be intriguing. PwrCor has engineered a proprietary novel heat engine using known thermodynamic principles that extracts more energy from heat than other technologies like ORC. So PwrCor can produce more power from a given heat flow than ORC can, or alternatively, PwrCor can produce the same amount of power from a smaller heat flow. PwrCor can effectively utilize lower temperature heat than these other technologies, and PwrCor promises lower capital cost and far better economics. In closing, PwrCor has identified a number of significant applications of the technology in both geothermal and oil and gas operations, as well as several other fields. Lastly, PwrCor has had the technology developed and tested by the Southwest Research Institute, which has specific expertise in this field of thermodynamics, as was evidenced in Kelsey's presentation. We now look to work with industry to deploy PwrCor in oil and gas operations. We thank you for the time spent with us today and are now open to field questions that you may have.
Thank you very much, Tom. That was a good one. Thank you for such an insightful presentation from you and Chris. There were some questions during the presentation I can read for you.
Sure.
Yes. The first question is, in addition to geothermal, what are the other vertical markets where your technology applies, apart from geothermal, in addition to geothermal?
Sure. So thank you for that question. Primarily from industrial process heat is where we're focused, and where the Department of Energy has identified the enormous amounts of low-grade heat in industrial processes. I mentioned that they can be harnessed from process cooling systems. So if you can envision a chemical process or refinery that has process cooling in it, a cooling tower or a dry cooler, PwrCor can intercept that heat and provide on-site power while reducing the overall power limit. So industrial process heat is one. We're also focused on reciprocating engines, both gas and diesel fired as well. Also, as related to industrial process heat is hydrogen and production in a form of electrolyzers. As the H2 dynamic of industry continues to gain momentum, we've modeled several hydrogen electrolyzers, both alkaline and PEM, and determined that we can extract heat from their internal cooling process to provide on-site power. To give you an idea of some of the other applications aside from geothermal.
Thank you very much for that response, Tom. The second question was, have any commercial contracts been secured that leverage your technology?
Not contracts for commercialization so much as a demonstration pilots. We have contracts for two. I mentioned for natural gas compression, for upstream natural gas application, as well as carbon dioxide compression, which will be used for enhanced oil recovery.
Thank you very much again for that response. To the third question, how long in hours has the uptime been on these supercritical CO2 turbines?
I'm not sure I follow the question, please.
How long in hours has the uptime been on these supercritical turbines?
Sure. So Kelsey can maybe address the mid to higher applications. And I can state that the Southwest Research Institute has tested our lower temperature supercritical CO2 for a total of probably 400 plus hours on site, as well as when it was deployed in the test facility in a geothermal well in Northeast California.
Yeah, so you're asking total operating hours, is that what the question was?
Yes.
Exactly.
Okay. So yeah, so on the high temperature stuff, I mean, we're a test facility, we're not an operator by any means. I think on the integrally geared machine, we probably have the most running hours on the turbine. I would say maybe 100 hours, maybe 200, something like that, where we're running, get it up to speed, up to temperature, up to pressure, run it through the day, shut down, right? So we haven't run anything long duration, basically just trying to prove out the technology.
Thank you very much for that response. The next question was, can you scale down from a few megawatts to maybe tens or hundred of kilowatt hour of kilowatt?
Sure. So our technology right now is geared for 350 to 500 kilowatts. If we're looking at the low temperature where PwrCor is focused. I can let Kelsey address how they might be able to go from high temperature megawatts to kilowatts. But I might say that PwrCor's technology enables, our design enables lower temperature extraction and conversion to power. And it is different than the higher temperature designs for supercritical CO2.
Yeah, so on the high temperature stuff, we can definitely cut power levels. You basically just cut your flow path on your impeller. So definitely doable. I will add to what you said, Tom, that I think for the PwrCor system, the idea is to do a modular scale up, right? So you said your base unit is 300 to 500 kilowatt range, but if you wanted, say, more, you could deploy 2 or 3 units in parallel. Is that correct?
That is correct, Kelsey, although we do envision providing megawatt units as well, 1 megawatt.
Thank you very much. Kelsey, I have a question for you, specifically directed to you. What is the likely magnitude of CO2 leakage in a system of this sort, of its similar magnitude to the ORC system?
Yeah, that's a good question. Are you talking about, well, I guess it'll be different on, say, a radial impeller system versus the PwrCor system because the core technology isn't quite the same. On, say, for example, the 3 megawatt geothermal skid that I showed, it'll be quite small. So on that one, we have a radial turbine running at, I don't know, 22,000 RPM, something like that, with dry gas seals. So the leakage across the dry gas seal is very small because you're running like microns clearance up between those, between your rotating face and your stationary face. I guess on the PwrCor system, I would let you maybe fill that because I know it's not quite the same, right? As far as leakage.
Right.
Okay. Chelsea, you still got another question here. Someone says, nice summary. What is the magnitude
What's the magnitude
what
for
is the
leakage?
main stumbling? Sorry, what is the main stumbling in the adoption of a supercritical CO2 Brayton cycle power generation system?
Can you repeat
What
the
was
first
your
part of it?
biggest stumbling block? Yes.
Sorry, kind of cutting in and out. Tom, did you catch the question at the beginning part of that?
No, I did not. If you can please repeat, thank you.
Sorry.
Okay. Kelsey, what is the main stumbling in the adoption of a supercritical CO2 Brayton cycle power generation system?
The main stumble. So I think for power gen, specifically if we're talking about the high temperature stuff, I think the main stumbling block that we found, say, on the turbine design initially under the Sunshop program, I think was managing thermal in the shop. So I mentioned this very briefly, but basically if you're running 700 C at your first stage of your turbine, and then, I don't know, 3 inches away, you have your dry gas seal. And your dry gas seal obviously runs with very, very tight clearances, so it's very sensitive to temperature. So I think their rated temperature for those guys is a couple hundred degrees. So trying to manage that thermal transition in the shaft from 700 C down to maybe 100 C over a few inches, that was very challenging. And then I think scaling up from there up to the step facility where we're trying to demonstrate the full cycle. I think the main challenges there have been equipment at scale, just because there's no assembly lines, right? There's no procurement paths developed for a lot of these things. So I think the biggest problem that we've had, and we still don't have one, is the high temperature turbine stop valve. So you need a valve in case of basically an ESD or a runaway situation. You need a valve, a control valve on the, I can't remember off the top of my head if it's upstream or downstream immediately of the turbine, but either way, you're running very, very hot. So you need a control valve that can manage that. So they were actually casting the body of that valve out of Haynes 232, I think, and having just a terrible time casting that part for the valve. So just things that are typically trivial because you can get them off the shelf. Some of those things don't exist yet for CO2 cycles, especially on the high temperature side.
Thank you very much for that. Our time is coming to an end now. We can end at that point. And we would like to give a vote of thanks to you two for that presentation. It was a very informative and very, very good one. It left us with a lot of questions that we are able now to see what exactly you are doing. Thank you very much for that presentation. We are much humbled to have been accepted our invitation to come and present.
You're very welcome, and thank you for the opportunity to present. Very much appreciated. Okay. Good day, everybody.